Welcome to the Arkansas Food Farms and Forests podcast, the podcast bringing you the latest on food, fiber, and forestry research from the Arkansas Agricultural Experiment Station, the research arm of the University of Arkansas System Division of Agriculture.
Welcome to Food, Farms, and Forests. I'm your host, Jennifer Fouch. Today we are learning about research that shows pesticides advance sustainable agriculture. The goal of this research was to assess the environmental footprint of pesticide use. To talk to us about this research is Marty Matlock. Dr. Marty is a professor in the Biological and Agricultural Engineering Department.
Thank you, Jennifer. It's an honor to be here.
So the study is titled Life Cycle Assessment of Impacts of Eliminating Chemical Pesticides Used in the Production of U.S. Corn, Soybeans, and Cotton. Is this the first study of its kind?
It's the first study to analyze the sustainability impacts of these important crop management systems.
And what were your key findings from this study?
The key findings are pretty self-evident for anyone who's been engaged in production of any crop from the land. That is, the chemicals that are used to reduce pest impacts have the consequence of protecting or even enhancing yield, allowing crops to achieve closer to their maximum potential yields. Reducing those insect disease and weed losses has the effect of improving the environmental impacts associated with those crops that are produced.
So they enhance productivity?
They enhance productivity. And again, it's to a certain extent, this is self-evident. This is why agricultural producers pay the money to buy these products to put them on their crops, is because it makes economic sense, because then they get more yield. The yield that they get is enough to offset the cost of the chemicals, or they wouldn't use the chemicals. Now, the economic values often are aligned with the things that we care about that are not economic, like water use, land use, greenhouse gas emissions, energy use, that are all encumbered in that volume of crop that we produce. So when you do something that makes that area, that makes all those inputs that go into making that volume of crop, whether it's a bushel, a kilogram, a bale, whatever that volume of crop is, if you do something that makes that more efficient, it has the effect of reducing all those environmental impacts that are the cost or burden of producing that crop as well.
So you found that not only are farmers then producing more, so they're making more money, they're saving more money, and then also saving on water, land, energy use, and then in turn, greenhouse gas emissions.
That is correct. And this is on a per unit of crop produced. We live in a global agricultural economy and food economy. So the consequence of not having access to these pest controls would be that it would take more land to produce the same amount of crops, or more water to produce the same amount of crops, or more greenhouse gas emissions to produce the same amount of crops, and energy to produce the same amount of crops. Some might ask, well, why would we need to produce the same amount of crops? Because there are 8.1 billion of us on the planet, soon to be 10 billion. We got 2 billion more people coming to dinner. We need more food to feed them. We're going to have to make sure we have enough, we can produce enough with the land we have. Otherwise, we will expand agriculture, which is to say we will convert forest lands, natural prairies, arable lands that are not in agriculture into agriculture in order to feed ourselves. And that will result in an enhanced biodiversity loss across the planet. So by freezing the footprint of agriculture, this is the World Wildlife Fund, Jason Clay of the World Wildlife Fund's concept, that by intensifying agriculture where we produce now and increasing yields where we produce now, we save land for other life. By saving land for other life, we enhance biodiversity, and we at least stop the decline of biodiversity. In that sense, there are multiple facets by which crop management tools enhance sustainability.
And for this study specifically, you looked at corn, cotton, and soybeans, correct? Those three crops.
These three crops, yes, because these three agronomic crops represent, oh goodness, about 70% of agricultural lands in the United States. And so they're the most significant from a land area perspective, and they have significant economic impact as well. We all understood that the framework for the use made sense, but we didn't have the numbers. We had not conducted the life cycle assessment to quantify how much impact and how much improvement we saw. And I will tell you, we were surprised.
You mentioned the life cycle assessment. Can you give us some background on how this research was done? Explain the life cycle assessment, and then maybe a little bit more into the categories that you looked at: the energy use, water use, and greenhouse gas emissions and land use. How did you get there?
Certainly, life cycle assessment is not complicated. It's just very tedious. Think of it as trying to understand all the inputs that go into making a product. So, like let's say a bale of cotton or a bushel of corn or a bushel of soybeans. Everything that it takes from extracting the iron ore to make the tractors, extracting the crude oil to make the diesel fuel, and the petroleum products that make the chemicals that make the pesticides and herbicides. All those things that go into consider all those little Lego blocks. So those little Lego blocks all stack up into a process flow. Those are called unit processes, and those are the process flows that result in that final bushel of corn. Everything upstream. Now we can take that bushel of corn all the way downstream to grave. So what I just described is cradle to the bushel of corn, which we call farm gate. So cradle to farm gate is the boundary we analyzed. Now, you can also analyze cradle to grave, which is where you see a lot of life cycle assessments doing, which is looking at the whole impact of any product or process. We were interested at farm gate because that's where the farmers make decisions. Beyond that, the farmers don't make decisions. So we wanted to give information to the farmer. So cradle, everything that it takes all the way to that bushel of corn, at the proper moisture in the grains drying bins at the farm before it goes to the silos and is sold. So that's what life cycle is. Now, every one of those little unit processes, every one of those Lego blocks has with it the amount of energy, water use, greenhouse gas emissions, land use required to produce that volume that went into making that bushel of corn. And so those are called encumbered loads in the unit processes. And those are all aggregated up to that and then analyzed for that bushel of corn. So that's what life cycle assessment is. It's a very tedious accounting method. It's not complicated, but boy, does it require a lot of data, because how much land does it take to produce a liter or a gallon of diesel fuel? That's a good question. And we have to answer that question before we can then figure out how many gallons of diesel fuel does it take to produce a bushel of corn. And then that land load goes into that corn, as well as the amount of area it takes to produce that bushel of corn. So you see how it all adds up.
About how long did it take you to complete this research?
3 years. The longest, most difficult part of any life cycle assessment is that data collection part. We call it life cycle inventory, finding all the information. And the reason is because you're never really done. You think you've got all the information, you run the analysis, and you find out the stuff that you really need you don't have. And so you have to go back and look further and look harder. Or the things that you think you know, you really don't know that well, and you have to get more information. Simple questions like how much nitrogen does a farmer put on the soil to produce a crop? We know what the agronomic demands are, but we don't really know what the farmers are putting on. We have sort of county level averages that we're able to use. So getting to that farm level data was important too. Rather than just simply analyzing a farm, we recognize that in the United States and around the world, agriculture is place-based. The impacts of location determine what you have to do to successfully produce a crop. And so we looked at, basically we created archetype farms, which are example farms in the top 10 top producing state for each of our three crops. And soybeans, we used 12 or 13, I think 13 total, because soybeans are so broadly produced. Michigan, for example, produces a lot of soybeans, not so much corn. Kentucky, soybeans, not so much corn. So we had to expand out our soybean production models. We used 4 top producing counties in each of those 10 top producing states, giving us 40 representative farms for every crop. And then you can't just analyze for 1 year. We had to simulate the production in order to get all the background information for what it takes to produce the crop. We had to use a crop production model, APEX, built by USDA Blacklands Research Center down in Temple, Texas. That's a well-respected crop modeling system that's been in use for 50 years. So we used that model, and then we did across all 40 representative farms for 6 years of production. So we got the highs and lows over that 6 years of rainfall and heat and drought and all the conditions that occur over what we would call nominally a normal 6 years. Farmers know there's no such thing as a normal year, but we didn't want to have, for example, 2011, 2012 representing our cropping years, because that was a 50-year drought. So we wanted to avoid that. So you see how complicated this gets real quick, and just trying to answer a question, what is representative of corn, cotton, or soybeans in the United States? There's a lot of corn farmers, over 350,000 corn farmers out there at any given time, and more than that, 400,000 plus soybean farmers at any given times. And they're making decisions every day based upon where they are, what is needed to produce that crop, and frankly, the price of the crop, that what they anticipate the price of the crop is going to be, so they can manage yield. They're not maximizing yield, they're maximizing profits. And so that's where these chemicals come into play. Sometimes it's okay to lose a little bit of your crop to a pest as long as your profits are protected. But it's not okay to lose your profits to a pest if you can afford to, if it's more profitable to manage the pest.
Would you say that finding that representation and making sure you were representing farmers well across the country was the biggest challenge in this study, or did you find any other challenges?
No, representation of the farmers' practices and decisions was the hardest part. There are a number of reasons. One, farmers don't just tell the world what they do every day. They don't have to. They're a business. They're operating within a legal framework and a regulatory framework and a cultural framework. They do report to the USDA on their Ag Census, National Annual Ag Census survey. And that Ag survey then aggregates to county level. That's why we use county level archetypes, because we know generally what a Washington County, Wisconsin farm looks like if it grows corn and soybeans in rotation. We generally know what, on average, that kind of farm in that location looks like. But one of the challenges we had, though, is that nitrogen application, for example, for corn, one of the most expensive and probably among the most critical inputs for the corn for determining yield, it's highly variable based upon previous year's conditions, based upon because if you grew soybeans the previous year, and many of them did, and then there's nitrogen carryover from the soybeans to the corn the next year, the amount of nitrogen applied is less. Or if corn prices are down and nitrogen prices are up, farmers are going to accept less yield in order to make more profit. So trying to capture that level of variability was key, because remember, the primary impact of not using these pest control chemicals is decreased yield. The primary impact of using them is increased yield or protection of yield. So if you protect the yield, but it doesn't make you more money, it doesn't make good business sense. So that's where we had to find that sort of balance that the producers have to make every season. We did the best we could. It's not perfect. It's a model. George Box, the famous statistician from the University of Wisconsin, said all models are wrong, some models are useful. We wanted this model to be useful. Of course, it's wrong. It's a model, but it's useful.
Very good. So it's useful for farmers, useful for scientists, and it shows some of the benefits of pesticide use. Now, when we say pesticides or when we say chemicals, for the consumer, that might sound like something scary. Are there any drawbacks to pesticide use, or what should, on the consumer side, people know about pesticide use?
Certainly. I mean, we use chemicals every day. We brushed our teeth this morning, I hope, with chemicals, and we shampooed our hair with chemicals. We cooked our breakfast and we ate our breakfast with chemicals. Chemicals are just simply the compounds that make up the things that make up us. What makes pesticides scary to the public is that pesticides are designed to kill things, right? They kill insects. That's called an insecticide. They kill weeds. That's called an herbicide. They kill fungi. That's called a fungicide. So disease control, weed control, insect control. The thing is, they're incredibly heavily regulated in the United States, not everywhere around the world, but in the United States. And the regulations are incredibly robust. So pesticides that are applied on the crops on the land are tested before they're certified. Now, we had nothing to do with that part of the study. There is a cost, a risk associated with the use of pesticides, and there's a cost, a risk associated with not using the pesticides. And what we were showing is the not using the pesticides. Our part of the study was asking, all right, we know that those risks occur. What happens if we just take them out? And that's really bad. What we showed is that's really bad. That will lead to really bad impacts: increased greenhouse gas emissions, increased water use for the food we eat, increased land use demands for the food we eat, increased energy use for the food we eat.
So in conclusion, the key findings, and you mentioned this too, some of the benefits that you found in your research. This is a very broad summary: increasing crop yields and decreasing consumption of natural resources.
That's correct. And decreasing emissions per unit of crop yield.
Why was this research needed, and why now? How did it come about?
Certainly. We're working, the research itself is funded by Crop Life America. Crop Life America is a business organization supporting policy and programs for agricultural chemicals. They have a vested interest in advocating for the use of chemicals. We do not. They came to us because we're independent scientists, and they asked us, can you answer this question? Is it bad to take these things from a sustainability perspective, to take pesticides out of these three crops? Why are they interested in that? With current discussions about sustainability and now the discussion about regenerative agriculture, especially our European cousins are looking at regulatory frameworks that demand the reduction or elimination of exogenous chemicals, that is, chemicals from outside production in crops. And it means no fertilizers other than manures, which are chemicals, by the way, and have chemicals in them. And no pesticides or herbicides. And again, those are well-intended concepts, but they're ill-informed because they don't understand what happens if you do that, which is that you'll have a collapse of the agricultural production system. It won't be profitable for farmers. And if it's not profitable, who's going to grow? Because the fact is, farming is a business. And so that's why they were interested. And we're interested because it's a reasonable scientific question to ask, and we answered it. And we have guardrails. If we ever do advocacy science, we lose our jobs. We can't get published, we lose our jobs. All of our work goes through external peer review, anonymous peer review, so we don't even know who's looking at the work to say if it's worthy of publication or not. This work, at this stance, will go through two peer review processes. A public peer review process for the life cycle assessment, which we've completed. Our life cycle assessment work it conforms with ISO standards, the International Standards Organization standards for LCA. So it's ISO conforming. We have that verification. Now we're moving to peer review publication. We'll be submitting the work for publication in journals.
Very good. Is there anything about the research, the benefits that you found in your results that I didn't ask that you would like to mention?
I was surprised by how impactful nematodes still are in agronomic production. Nematodes are still one of the major yield impactors unmanaged on the land. This is a big challenge. And the problem is that the biggest control we have for nematodes is cold soil. Cold soil reduces their density, it freezes them. Well, our soil's not getting that cold anymore for as long because of climate change. And so that's just one example of how climate change is going to have so many impacts on our farmers' ability to actually profitably and sustainably produce the food we need.
What do you hope to see in the future? You mentioned that you want this to be useful to the right people. Where do you envision it going? Where would you like to see, as a scientist, as someone who worked on this research and you got those results? Where would you like to see it in the future? How would you like it to be used? Where do we go from here with the results you found?
I think the most important sort of big general contribution this research makes is it shows that we can measure the big so what consequences of our decision making. We don't have to just guess, we can measure them. And so this illustrates how, in one way, and a very effective way, we can measure the consequences of a collective decision.
Who were your collaborators on this research?
This research was sponsored by CropLife America. Our collaborators were Greg Toma at Colorado State University and Kyle Lawrence, a master's student at the University of Arkansas.
Marty, thanks for joining us.
I'm glad you're doing this. I think podcasts are critically undervalued as a communication tool by the universities.
That was Dr. Marty Matlock, who is a professor in the Biological and Agricultural Engineering Department. Thanks for listening. I'm Jennifer Fouch. Don't forget to subscribe.
The Arkansas Food Farms and Forests podcast is produced by the Arkansas Agricultural Experiment Station, the research arm of the University of Arkansas System Division of Agriculture. Visit aaes.uada.edu for more information.